Hi everyone. Uh, thanks to the organizer for giving me an opportunity to speak here. I'm Aung. I'm a graduate student at Yale University, and today I will present ongoing work on the cold gas streams and their evolution under the self-gravity, together with the work together with the Nia Mandaka, who is the previous speaker, and Daisuke Nagai. So, as you may have heard from the Nia's talk, these gas streams are the main mode of accretion for the high redshift galaxies and the low redshift clusters. And these cold gas streams, the study of these cold gas streams are important because these provides the main fuel for the star formation. These gas streams come from the cold environment, and then these can carry the cold gas directly to the center of the galaxies where the star formation can happen. So these gas streams usually have like a high density contrast compared to the halo gas in the background, and also like it's very supersonic with respect to the halo, which Nia has already shown. And from the observations and the simulations, people have shown that there are gas clumps in the center of the galaxies, which provide the sites for the star formations. And there have been claims that these clumps may come from the fragmentations or the clumping from the filamentary gas structures. And these streams can be destabilized by the KHI, as Nia has previously shown, and which can lead to these clump formations. But Nia also shows that there can be the gravitational instability, which can introduce these clump formation as well. But what will happen if we combine the KHI and the self-gravity together? How will they interact between these two instabilities? And so this is the topic that I will mainly talk about. Previous studies have shown that if you have a KHI and a self-gravity, the self-gravity can stabilize the KHI. It has been shown for the spherical geometry, where if your mass does not exceed the Jeans mass, the KHI will get stabilized by the self-gravity. And then if the mass exceeds the Jeans mass, of course, it will collapse due to the self-gravity. For the gas streams, the analog for the Jeans mass will be the critical mass by unit length that is derived by the Jerry Ostrager and other people. And in this case, if the mass by unit length of the streams exceed this critical value, there will be gravitational instability that will lead to the deformation, that will lead to the collapse of the stream. However, there's more complications because of as shown by the Hunter et al. Papers, that there can be new mode of instabilities due to the self-gravity if you have the interface with different densities. This is not due to KHI, not due to the Rayleigh-Taylor instability, but additionally new mode that will get introduced too. A few notes that about this instability. This will not arise in the spherical geometry. So that's why the previous study by the Murray et al. That I talked about do not show that, only show that the KHI will stabilize KHI will get stabilized due to self-gravity, but there's no new mode because they only explore the spherical geometry. And in addition to the gravitational collapse, if you exceed the mass by unit length of a critical value, this instability can develop even if the mass by unit length is lower than the critical value. And then there's no shear needed as compared to the KHI. And the only thing that is needed is that there is some sort of interface density contrast between the two medium. If you want to know why it develops, a simple physical intuition is that if you have two fluids that are at the interface of each other, it's not the minimal energy solution, and so the solution will tend to mix. Thanks to Yuval for this great insight on the. So So let's go to the simulations, and that is all the derivations that is shown in the paper, in the theory paper, is just the linear evolution. So what will happen if we go into the linear regime? We want to study it in the simulations. So we use the Ramsey simulations to do that. So here I will show the mass by unit that is 10% of the critical value. So it's the gravity is really weak. And you will see that the KHI dominates for this kind of streams. And the evolution, as you may see here, is very similar to the simple evolution by if you have the KHI only. I'll just let this go for a while. All right. But what if you go to the 90% of the critical value, like if you increase the mass significantly, and so the gravity is a lot stronger right now. So what you will see here is that in the early phase of the streams, similar to the spherical geometry, the KHI will get suppressed due to the self-gravity. So you will not see the similar form of violence in the initially, like as compared to the previous simulations that I showed. But at late times, the new mode of instability that I talked about by the self-gravity will take over. So as you can see here, it's like in the early phase, the stream is very stable, but right now, like there's a big clumps forming. That's due to the new mode of instability. The collapse wavelength that is predicted from the linear calculation will show that the wavelength will be larger than the approximately 6 times the stream radius. And that's why we're seeing the full clumps along the 32 stream radius. It's about the 8. The wavelength is about the 8 times stream radius. So how do we know when the streams will fragment due to the KHI or the clump due to the new mode of instability that I introduced? Well, we can do a simple comparison of the time scale. Like then the time for this new mode of instability to take over is on the order of a free-fall time times a few factors. And then we can compare that to the disruption time scale by that is shown in previous talks. That is due to KHI. And you can see that if you have the density contrast, if you have the Mach number of about 1, if you have the mass by unit of 30% of the critical value, it will usually collapse due to this new mode of instability. And the simulations agrees with this method of analysis. So what will happen? So let's talk about some of the clump properties that in the simulations that shows the clump formations. So most of the mass of the clumps usually oscillates, but and then plateaus over some mass. And as you can see, for the large mass by unit length streams, there will be a higher mass compared to the Jinks mass. But most of them are on the order of Jinks mass, but do not necessarily exceed the Jinks mass. The Mach number of the turbulence. Most of the like from the mass by unit of 60% to 90%, the evolution is about the same. And the turbulence in the clumps quickly dies down over time. But you can see that for the mass by unit of 40% of the critical value, there is some difference in the initial phase. This is due to as I've shown previously, if the mass by unit is really high, like 90% of the critical value, the KHI gets suppressed really heavily, and there is no KHI in the early phase. But if it is 40%, the KHI did not get suppressed as much as the 90%, and so there will be a large turbulence introduced by this KHI. Because of this large turbulence, the visualization parameter is also large for the low mass by unit streams as well. But except that, all the other streams are usually visualized. So to conclude, the streams of all scales that we have explored can fragment either through the fragmentation by the KHI or they can form clumps due to the gravitational instabilities. Depends on the stream parameters, like whether you have a weak gravity or the strong gravity. Which means that the case is that even though like some studies would predict that self-gravity can suppress KHI, if it can suppress, its own instability will take over to form clumps. So future work will look into the effects of the gas cooling. If you have high density clumps, the cooling time will be shorter, and so the cooling will accelerate it, and the properties can change based on that. And we'll also look into the study of how it will impact the star formation and the gas structures in the high redshift galaxies. So, thank you.
Time for quick questions. Next speaker set up. Any questions?
I wonder if you have a filament, then it fragments if its line mass is above a critical line mass. So in your streams, maybe they would fragment anyway. You know, if they are above the critical line mass, they fragment whether you want it or not. Then the fragmentation has nothing to do with these instabilities at all. It's just simply competition. You know what I mean? So is the fragmentation triggered by the instability, or is the fragmentation something you put in as an initial condition because you have an unstable stream? You know what I mean?
So we set up the initial condition so that the stream is in a perfectly hydrostatic equilibrium.
Yeah, but you have small fluctuations grow quickly. It's like a cheese instability or whatever, like an instability. Just look it up. There's a critical line mass above which a little fluctuation will immediately grow and lead to fragmentation. And you go.
Right. So we also run a simulation that is set up in the without any part of for the adiabatic streams, and we found that the fluctuations in the density for like 40% of the stream mass do not go over this critical value, no matter how large the perturbation is. For the 90% of the streams, it does go over sometimes, but for as low as 40%, which we see the fragmentation in the station, it does not go over that. So cannot be because of that.
Yeah, just to follow up on that point that Han made, the new thing here is that this fragmentation can happen even if the critical line mass is even if the line mass is well below the critical value. He finds fragmentation with a line mass that's only 30% of the critical value. And it's not driven by the Kelvin-Helmholtz induced fluctuations in the density. As Han just said, we checked that, and the density fluctuations induced by Kelvin-Helmholtz are not nearly strong enough if your line mass is only 30 or 40% to drive you above. This is a new type of instability, which I think anyway is very interesting.
Okay, let's thank speaker again. And our last speaker before the break.